So to sum it up, what we have discussed so far, the Big Bang produced only hydrogen and helium and no other heavy elements. There were just a little bit of heavier ones, but you can pretty much ignore them. So to a good approximation, just hydrogen and helium. And that led to the formation of some first stars. And inside the stars, you formed bigger elements like carbon, oxygen, silicon, all the way up to iron. And as long as these elements are stuck inside the stars, we still don't get to use them to form a body. So it doesn't explain where we came from. But fortunately, as you saw on a previous a few minutes, these stars can actually explode at the end of their life, and that would release a lot of stuff back into the outer space. And then what had been synthesized at the core of these stars get released, like carbon, nitrogen, oxygen, iron, that eventually formed a body. So what is believed is that our sun is probably the third generation star. So it had the initial stage of the star formation based on hydrogen, helium alone. Some of them exploded, released the more stuff. You accumulate them, form the stars once again. They also reached the end of life, exploded, and the sun used that kind of material to form the initial core of the star, and that led to our own existence. So the explosion of a star like this is very important because that would be the origin of our own existence, origin of some Nobel Prize as well. And so we are literally stardust. So we came from the star, and that's what we are actually made of. But of course, you should still ask the question, is that really true? Is there any evidence for that? So at least we can observe some of the past supernovae that happened nearby in our own galaxy. So this is the famous one called Crab Nebula. It is believed to be a remnant of the past supernova that happened actually fairly recently in the year 1054. The reason we know the year is that there is some historical record in old Japanese literature by Teika Fujiwara. And in this old manuscript, you find a reference to a supernova. What it literally says is the guest star. There is a star he could see, which wasn't there before. That's why it's the guest star. And that was the supernova explosion. And these days, you can study the same object in many different ways by using optical telescope. That's the usual telescope. You can observe X-rays. You can use infrared light, like when we talked about seeing the black hole at the center of a galaxy. And radio, which we have used also for to observe the Big Bang itself. By combining information from these different techniques, you can get a better understanding of what's going on inside this object. And this is a time sequence of the X-ray pictures coming from Chandra satellite. By putting that into a movie file, you can see that there's still a throbbing going on. So this happened like 1,000 years ago when it exploded, but it's still releasing material that you can see in this throbbing, this looped movie. And so you can see that the supernova does release material into space, and that's how we came to exist. We believe that something like that is going to happen soon, actually fairly nearby. Do you know which star is Betelgeuse in this picture? You probably can identify Orion, constellation Orion. So Betelgeuse is on the left top corner of this Orion constellation, and it weighs as much as 20 times the mass of the Sun. It's fairly nearby. It's only 640 light years away. So by now, listening to my lectures, you would immediately notice that this is actually a very close distance on the scale of the universe. And if the star is this close, you can even measure how big it is just by looking at it using telescope. So this is the data that shows that the apparent size of Betelgeuse has shrunk by 15% in mere 15 years. So something is really happening with this star. So you can even observe the surface of the star when the star is so close. And what you see in this picture here is that the surface is also really throbbing now. You see parts that's sweating up. You see parts that's sinking in. So you see the surface is very dynamical at this moment. So that really shows us that something's going to happen to this star pretty soon. Pretty soon in this case may mean the next 10,000 years. But, you know, explosion may happen tomorrow as well. We don't really know. We can't predict. But it's clear that this is going to happen sometime soon into a big supernova. So putting things in perspective, the way we can tell how old a star is and what is the star is made of, what we can do, again, going back to this, the sort of prism, by measuring the spectrum of colors coming from the star, you see these lines which shows some colors are missing. And this is called spectroscopy, which is a very important technique in studying the astronomical objects. So this particular star, which is actually our sun, has a lot of these lines, which shows that it has many heavy elements. So these stars are called population 1. A lot of metals, elements heavier than helium. So this is clearly contaminated by the past supernova explosions. If you look hard enough, sometimes you find stars which seems much cleaner, less contamination of these heavy elements. So they are called population 2 stars. If you go way back into the beginning of the universe, there must have been what is called population 3 stars, which are made of hydrogen and helium alone, without any contamination from the previous generation of stars. We haven't found those, but people are still looking. So now it comes to this question, how do we know that Big Bang produced hydrogen and helium, but not more? We need a different tool. As we talked about, what we can look back to the point when the universe was only 380,000 years old by using radio telescopes, because we can detect the cosmic microwave background, which is the light coming from the Big Bang itself. We talked about it. But there's a wall, right? You can't go beyond that using telescopes. We can't see through that wall. We need some different technique to understand what's going on at the earlier moments of the universe. So we use a different tool called particle accelerator. The idea is very simple. The universe is so dense and hot, we would like to understand what happened back then. So that's something we can try to do in our own laboratory. We try to create an environment where similar reactions can be created artificially, which must have happened early on at the beginning of the universe. So that way, we can go back to the moment when the universe was only 3 minutes old. What we do is bring in literally neutrons and protons together, smash them against each other, and see if they can form something heavier, like helium. So we can try to redo this kind of reaction that happened right after the Big Bang in our own laboratory. And that's the way we try to go beyond this wall of 300,000 years old universe. So by studying these reactions in the laboratory, you can measure the probability for a reaction like this to happen. And once you measure that, you can make a prediction on how much of the helium must have been synthesized at the beginning of the universe. And that process is called Big Bang nucleosynthesis. And that will give you a prediction that the ratio of hydrogen to helium in a universe must be roughly 3:1. And indeed, you can measure the ratio of hydrogen and helium by looking at, again, the spectrum of light coming from the faraway objects. And this 3:1 ratio agrees very well with the observation. So that's how we can compare what you would predict based on what you learn from particle accelerators versus what we can actually go back and see using telescopes. And if they match up, that would give us a confidence that we understand what happened in the Big Bang itself. So by putting these information together, and you can put them in a computer and simulate how the first stars had been born. And we'll come back to this later, but at the initial stage, you don't have that much concentration of gas. You have sort of a big blob of dark matter. We briefly talked about it in the first lecture. Once you have this blob of dark matter, gravity pulls the ordinary gas in, and it starts to form this cloud of gas, called the molecular cloud. And the core of the molecular cloud further collapses and start producing something rather dense, and that would eventually become a star. You can reproduce this process in a computer these days. And if you go further with this computer simulation, then this initial form of the star would start to accumulate more stuff from outside by the gravitational pull. But once they start to accumulate so densely, then it starts to actually eject it off. It will sort of blow it out by the reaction. So that's something you can see in this computer simulation. So for a while, dust just settles on the surface of this protostar. It's not quite a star yet. But as they keep accumulating on the surface, you see this ejection of material in the polar direction. So it stops growing at that stage because whatever settles in further gets blown out, so the stars wouldn't grow anymore. So what you learn is that the first stars can grow only up to like 40 solar masses. But that is big enough to synthesize elements all the way up to iron at this stage. And that's how I believe that initial elements had been synthesized inside the stars. So going back to the discussion we had at the very beginning, we start only with hydrogen and helium. So we asked the question where we could have possibly come from because we need carbon, oxygen, and so on. And the answer turns out to be that they were built in stars, and we are the stardust. But you might have been listening carefully to me and asked the question, well, you told me that we can go only up to an ion. Can't go beyond that because you can't release energy by shedding mass beyond iron. That's at the bottom of this curve. How can you further climb up the hill? And we of course know that there are elements that are heavier than iron, like what you might buy in a jewelry store. So we need a mechanism to produce those elements as well. And indeed, if you look at the so-called abundance of these elements in the universe, and you do see all these heavier elements like silver, gold, platinum, lead, they must have been produced somewhere. And it's the nature of the science that you don't have answers to every question yet. They're still yet to be studied. We don't quite know where they came from. Many of us think that these heavier elements have been formed when the star is exploding. We talked about elements synthesized at the core, explosion releases. But explosion itself may bring the reaction even further. And explosion is such a dynamic process that you can even put energy in to let the reaction happen. So presumably, that's the way these heavier elements have been formed. But we don't know for sure yet. So that's where you might be able to provide further studies to prove this idea. This is yet another curious fact, if you think about this. A lot of important things have been explained by the property of these individual particles coming in together, like protons and neutrons. What we know is that proton and neutron have very similar masses within only like 2 per mil. Basically, they are exactly the same mass to a good approximation. But if you think of possible universe where the proton may be, say, 20% heavier than neutron, heavier equal mc squared means more energy. So proton can then release energy by turning into a neutron in that case. So all the protons end up decaying in neutron if it is heavier by 20%. So if that's the case, even if you manage to synthesize like a helium nucleus, protons inside the nucleus would decay into neutrons. They're all electrically neutral. So you don't end up with anything that can become the atomic nucleus at the end of the day. So no atoms will be possible at all. So the very existence of chemical elements actually hinges on the fact that proton and neutron are pretty much the same in their masses. So that's another mystery we don't quite understand. Why are the masses of particles designed in such a way that somehow all these important things that would sustain our life had become possible? And another question, of course, is that even if you do manage to form these atomic nuclei, you still need electrons to go around them to form atoms. So how were the atoms possible? Why was that possible? And that's the next question about the Higgs boson.